Okay, this is the lesson 1.3 supplement in the AP Calculus BC course. If you're watching this in the AB course, then this is, I think, a supplement to lesson 1.6, so you should watch it before doing lesson 1.6. So here's a new limit concept that I want to talk to you about. Hey, let's say I had three functions. F of x is the lowest of them all, the smallest. G of x is the one in the middle, and h of x is the one that is bigger or equal to it. Now you're thinking, what happened over here? That's not bigger. True. So I have to specify that this is always true when x is near some value of a. So if my value is a over here, this is not really close to a at all, so I don't really have to worry about that part of the graph being below, as long as the part near a is above. So if the limit as x approach to f of x, the lower function, is L, and if the limit as h approach to x, at x approach to a, is also L, then what conclusion can you make about that middle function? I hope you can say that the limit as x approach to a of the middle function also equals to L. And if you can understand that, you understand the idea of the squeeze theorem, or the sandwich theorem. Okay? And this theorem comes in handy when we want to find limits, especially if we can bound them from a higher function and also bound them below by a lower function. So looking at example number 1, I've got f of x, and I've told you it's bounded below by 5x minus 6, and bounded above by x squared plus 3x minus 5, for all x bigger or equals 0. I want you to find the limit as x approaches to 1 of f of x. Well, it's probably good if we can actually just find the limit of both the lower function and the higher function. Thankfully, these are all polynomials, so I can just plug them in. Yes, nice and straightforward. No holes, no asymptotes, all those ugly things that we had to deal with from before. 1 squared plus 3 minus 5. I think that's also negative 1. Ah! Both the lower and upper limits are the same. So, I'll say something like this. Since the limit as x approaches to 1 of the lower function and the limit of x approach to 1 of the upper function both equal negative 1, then by the squeeze theorem, and you should quote it, that's like your proof, we know that the limit of f of x must also equal negative 1. Ta-da! Okay? That's a pretty straightforward example. I gave you the lower and upper. For number 2, though, I've asked you to show now that this limit as x approaches to 0 of the function x squared times sine of 1 over x equals to 0. So I gave you the answer. Now you have to show it. And in this case, it's your job to come up with the two lower and upper functions. Now the key thing about this is, notice I'm multiplying x squared by sine of 1 over x. Now, those of you who did the pre-calculus course, which should be all of you, hopefully you remember what the equation or the graph of sine x looks like. Yeah, it's an oscillating function with the largest value being 1 and the smallest value being negative 1. So this is sine of 1 over x. Doesn't matter, it's still sine of something. This can be as big as 1 or as small as negative 1. Which means if I were to look at a function that perhaps can bound, well, that's what I just said from above, right? And now if I'm thinking, I'm not looking at sine of 1 over x. Sorry, actually I said this originally, right? Sine x first, my fault. Then we change the x to 1 over x, but still it's a sine function, so it doesn't really make a difference. It's still going to be bigger than or equal to negative 1, and smaller or equal to 1. But now if I were to multiply everything by x squared, because that's what the function I'm really looking for, right? That would mean I'd have to multiply both the negative 1 by x squared and the positive 1 by x squared. And therefore, now, if you think about it, I've got this expression. Negative x squared is less than or equal to the function that I'm trying to find the limit of, and big less than or equal to x squared. Why is this helpful to me? Well, now I've squeezed the function x squared times sine 1 over x in between the negative x squared and the positive x squared. And now, of course, if I were to take the limit of both the lower and upper functions, you guessed it, they are both equal to 0. And then, since the limit of the lower function and the limit of the higher function both equal to 0, you got it, by the squeeze theorem. The middle function, which is x squared times sine of 1 over x, the limit of that as x approaches to 0, must also equal to 0. And there you go. I've shown it. Now, I also said verify with the graph. So if you have a graphing calculator, you can pull it out. But I'm just quickly going to use Desmos right now because I don't have my graphing calculator with me. And if I were to actually type this in, let's see my two functions. Y equals to negative x squared. There we go. I need another one now. What's my other graph? Oh, yes. Y equals x squared. Yes. Oh, I need one more, don't I? Yeah. The middle function. Y equals to x squared. I need a sine. Ooh, I need a 1 over x. Wow. What kind of crazy function is that? So you see how I've got my lower and my upper, and the 1 is always in the middle. Now if I were to zoom in at x approaches 0 to see what happens, yes, hopefully you can see that, yeah, they do sandwich each other, and the limit does equal to 0. Okay? Alright. Turn the page in your notes. Those of you in the AB, you don't have this example number 3. I think I just told you the result afterwards, so you can skip this part if you want. But those of you in the BC class, I'm actually going to try to do this little proof for you here. Okay? So I want you to consider this circle. It's a unit circle, radius 1, centered at the origin, and there's an angle of theta radians, yes, where of course the angle theta is an angle between 0 and 90 degrees, or pi over 2, in the given diagram. Okay? Now what I'd like us to do is, can we consider the areas of the right triangle OAD? That's this one. Okay? The sector OAC. The sector is like a slice of pi. And finally, the right triangle OBC. There's a bigger one. Okay? And I want you to show this statement. And by the way, this statement should have less than or equal to. My apologies. Okay? Show that cosine times sine is less than theta, which is less than sine over cos. Oh, okay. How can we do that? Well, I said consider the areas. So remember, when we're looking at a point A that's on the unit circle, this horizontal distance of x can be defined as, do you guys remember using the angle theta? Think back to like pre-calculus 11. Yeah, cosine theta. And how about the corresponding y value here? Hope you remember, this is like the opposite side. Yeah, sine theta. So if I think about the area, okay, of triangle OAD, it's 1/2 times the base, which is cosine theta, times the height sine theta. Look at that, cosine theta, sine theta. Okay, well, we know that's smaller than or equal to that slice of pi. That slice of pi being the sector. Well, how do I find the sector area? Here's your idea back to pre-calculus 12, I hope. Noticing this is a sector or a piece of the pie. Remember, if I go around the full circle, the angle measurement there is in radians of 2 pi. Please say you remember that. And so if I took a ratio of the entire area of the circle, it'd be theta over 2 pi multiplied by the area of the circle. Area of the circle is just pi r squared. Okay? So this is a proportion of the entire circle. That makes sense? Good. And this is supposed to be less than or equal to sine over cosine. Where did that come from? Well, I guess we need to find the area of the blue triangle. We know that OC must be 1, so the base is 1. The question is, what is the height, this BC length? And if you don't know the height, what I could do for you is just draw this out, and then let's say call this H. And then I want you to draw a similar triangle, oops, a similar triangle next to it, the one in red, 1 sine theta, cosine theta. And if I were now to try to use similar triangles where the ratios of the sides are equal, so H, what is H, height over 1, right, the ratio of the height with the length is equal to sine theta over cosine theta. Well, that's great, because that means height just equals to sine theta over cosine theta. And that's what I get here. So that's sine theta over cosine theta. And why is this going to be helpful to me? Because this, once again, is the area of right triangle OBC. Let's see if we can simplify some of this. I see half, 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 goodbye. Over here in the middle, pi, pi, goodbye. So look at what we have. What's left over is just cosine theta times sine theta is less than theta, which is less than sine theta over cosine theta. Ta-da! You've just shown it to me here. Bravo! Now, why are we even doing this? Because I want us to really look at this limit. Let's look at the limit as theta approaches 0 from the positive side, okay, of sine theta over theta. Why am I choosing 0 from the positive side? Because my diagram up here only said that this is true from 0 to pi over 2. Okay? Well, how am I going to use this? Well, this is part of the squeeze theorem. Can you not see how the theta is squeezed in between two things? But you're like, that's theta. I want this expression sine theta. Right. Okay, so we don't actually have that, but we have something close, don't we? Let me just write it down again. Aren't we pretty close to having it being equal to sine theta over theta? I want this middle thing to be like sine theta over theta. Well, maybe what I can do is actually divide both sides by sine. Let's do that. I know you're like, but that's opposite. I know. Just look. So you're now left with cosine theta, theta over sine theta, 1 over cosine theta. Agreed? Now, this is nice because it's almost exactly like sine theta over theta, but if I want it to be sine theta over theta, I'm actually flipping it, or I'm dividing it by itself, or 1 over. And when I do that, when I divide inequalities, do you know what happens? Yeah, the inequality sign actually changes. Think about it. 3 is less than 4, less than 5, right? Let's flip it. So 1/4. Is that still less than 1/3? Or sorry, is that bigger than 1/3? And 1/4 is less than 1/5? You then have to flip it, change the sign. Same thing there. Okay. Now, if I want to rearrange this because I like having the lower function on the left, okay, I will rearrange and say cosine theta is less than or equal to sine theta over theta, which is less than or equal to 1 over cosine theta. Once again, why is this important to us? Now, I hope you can see, let's apply the squeeze theorem. And if I ask you now to take the limit of 0 plus of cosine theta, you got it, that's 1. If I asked you to take the limit of theta equals or approaches 0 plus of 1 over cosine theta, you got it, that's still 1. So therefore, what do you know? Yeah, by the squeeze theorem, the limit as x, theta approaching 0 to the right of sine theta over theta must also equal to 1. And this is a very important fact. Now, let's continue on, because I only did it from the right-hand side. This is a one-sided limit. Oh, what's this idea? Even, odd. Remember the summer work that you were supposed to have done? Can you figure out how we're supposed to figure out if it's even or odd? Yeah, if the original function is this, what do we do to test it out? We put in negative theta in this case. What happens when we plug in negative theta? I'm getting excited. Uh-oh, maybe I'm not getting excited. What's this? Sine of negative theta. What is that? Think back to good old times in pre-calculus 12. Here's your graph of sine theta, right? What does negative theta do? That's a reflection in the... That's right, the y-axis. So I get this now, right? Or if I continue, I get this. Well, isn't that exactly the same thing as a reflection in the x-axis, taking this part? So really, this is equivalent to negative sine theta, because a reflection in the y-axis of the sine graph is exactly the same as a reflection in the x-axis, but being negative. So, we get this. So, those two negative signs then cancel each other out, and you get this. And that is exactly the same as above. So therefore, this is an even function. So since this is an even function, see, I gave you a hint here, an even function, then of course the limit of 0 minus of the function will be the same as 0 from the right, because it's a reflection in the y-axis. And if that is equal to 1, then the limit as theta approaches 0 from the left, that must also equal to the 1. Since the left-hand limit is 1, since the right-hand limit is 1, therefore the limit at theta approaches 0 must be equal to 1. And this is a very common limit that will be used in the questions that you have to do later on. Okay? It also comes in handy when we're talking about trig derivatives. Someday soon. Okay, so I've got 3 examples I want to do with you, and then after that, you're on your own to try some other ones. So these all use that lovely expression that I just proved for you earlier. And those of you in the AB class, I guess you're lucky you didn't have to write that all down. So the limit of theta approach to 0, you should write this down though, of sine theta over theta does equal to 1. Now, I also want you to know that because it's equal to 1, and only because it's equal to 1, I can actually reverse it or flip it. Yeah, and this will also still then, of course, equal to 1, because the reciprocal of 1 is 1. Okay. How do we do example A? Interesting how this is 4 theta and theta. Now really, I'm saying that sine of blah over the same blah equals to 1. Unfortunately, it's not over the same thing. It's sine of 4 theta over theta. They have to be the same thing. So what I need to do is make the bottom 4 theta. I can't just arbitrarily put a 4 in there like that. That changes the value of the question. So I need to multiply both the top and the bottom by the 4. And if I do that, then I can take out the constant 4. And now this is the same thing as the limit as x, or theta, sorry, approach to 0, of sine of 4 theta over 4 theta. Why is this nice? Yes, these are exactly the same thing. Now I can apply that limit that we just did. We know that this entire limit, because theta is approaching 0, then must equal to 1, and so our answer here is just 4. Okay? Alright. Part B, you're like, okay, these are two different things. Yes, they are. Very good. Remember our idea once again, we need to make it so that the blah 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 is the same thing at the bottom. Well, let me just separate them first of all, okay? I think that might help. Because what am I missing here now in the bottom? Yeah, it's a 7x, which means I need to multiply both the top and the bottom by 7x. Great! But what about the 1 over 2x? I can't really plug in 0. Sine of 0, 0, 1 over 0, undefined. So, yeah, that's where I told you this. We can flip it around too. So, what do I need for my blah, blah, blah over here? I need an extra factor of, yes, 2x. Because now that matches up with the sine 2x. But, of course, because I multiplied the numerator by 2x, I also need to divide by 2x. Okay? So, for part B now. The 7x over 2x simplifies to 7 over 2. Now I have the limit of sine 7x over 7x times 2x over sine 2x. The limit of two things can be split up into two separate limits. And then I'll find the product of those two separately. And I hope you can see that now this just equals to 1. This also equals to 1. So 7 over 2 is my answer. Beautiful, beautiful, beautiful. Okay, part C. You're like cosine, but I'm only dealing with sine. What? How am I supposed to figure out something with cosine in it? Think back to pre-calc 12 again. Yes, that course that you learned all those things. You're like, what's it for? You're using it all in calculus. So I hope that you can visualize this and think, I need to multiply this by the conjugate perhaps. And you're thinking, why would I do that? Let me show you, because if you do, you get cosine squared theta minus 1 in the numerator. And I will just leave the denominator as is. What's so great about the numerator? Yes, that good old Pythagorean theorem. And if I were to move the sine squared to that side, the 1 to the left side, I'll get now cosine squared theta minus 1. So that just equals to negative sine squared theta. I will now make that substitution, and you're like, so what? Well, I'll tell you what. I'll tell you what. Once again, I'm going to try to use that expression, right? How about sine theta over theta? Taking one of these and that. I know I still have another sine theta on the top. Okay. What I do know now is that I can take out the negative. I can then apply the limit to the two things separately and calculate them to find the answer to this question. Yes, this equals to 1. Negative 1, good. And then now if I plug this in, sine of 0 over cosine 0 plus 1. Sine of 0 is just 0, so it doesn't really matter what cosine 0 is. I do know it's 1. But nonetheless, the answer is 0. And there you have it. Okay. So notice I'm using this expression of sine blah 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 over blah 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 as the theta approaches to 0 equal to 1 quite a bit. And we got that by application of the squeeze theorem. So hopefully now you can try the rest of these problems yourself, and then you can double check your answers with what I've posted online. Alright, get to work.